Hi everyone, my name is Zhuoyuan. Today I will present our work. It's an analysis of LEO satellite network resilience, focusing on critical satellites. The advisor of this work is Morty. Let's start. Low Earth orbit satellites are a promising solution for connecting remote areas. It also has lower latency because it's closer to the ground than GEO and MEO. LEO satellites have some important parameters. The altitude, which impacts how fast the satellites move and how much area they can cover. The number of orbits and the number of satellites per orbit tell us how dense the satellite network is. Lastly, the inclination is the angle between the satellite's orbit and the Earth's equator. To summarize our findings, satellite utilization varies widely. Many satellites, especially over oceans, are underutilized, where usage is high in densely populated regions like Asia, Europe, and North America due to ground station density. Interestingly, satellites over the Northern Pacific and Atlantic are heavily used, driven by the constellation's inclination that directs traffic through these areas. And when those frequently used satellites are removed, increased loads will be put on other satellites. In the past, satellites can only talk to ground stations to deliver information, also known as bent pipe topology. But now, the emergence of the inter-satellite link greatly improves the performance of the LEO constellation. Inter-satellite link is a technology that allows direct communication between satellites. ISL has many advantages. It can reduce the dependence on ground station, reduce the delay, expand the coverage, and improve the reliability of the network. However, routing data using satellite-to-satellite link face the challenge of possible middle-hop failure. For example, some satellites lies on the routing path are broken. There are many reasons for the damage of LEO satellites. Malfunctions and scrapping, spacecraft collisions, military attacks, and extreme space weather such as geomagnetic storm. For example, in February 2022, due to a geomagnetic storm, 40 Starlink satellites are damaged. This is our experimental setup to explore the question. We choose two typical shells, Starlink Shell 1 and Cooper Shell 3 as our study cases. Starlink Shell 1 has a 53-degree inclination and denser, providing broad signal coverage. In contrast, Cooper Shell 3 has an inclination of 33 degrees, with fewer satellites, primarily serving low-latitude regions. So, if the critical satellites are broken, what exactly this impact will be and how it will influence the overall network performance? We have no idea for that. Therefore, our research question came out. If some of the highly utilized satellites are disabled, what would be the cascade impact on overall LEO constellation network performance? To conduct our research, we use the Hypatia simulator, which models the movement and communication of satellites in orbit. To simulate real-world usage, we choose the top 100 populous cities on Earth as ground stations. Our traffic are all the ground station pairs communication and perform a simulation for 200 seconds movement of the LEO constellation. We calculate transmission routes based on the shortest geographical path over the grid topology. Here is the grid geographic features of Starlink Shell 1 for one time step. In this figure, each red dot indicates a LEO satellite. The size of red dot is proportional to the satellite's usage frequency. Larger dot means higher usage. The blue X symbols represent the ground station on Earth. There are some key takeaways. First, ground station density influences the satellite's usage frequency, particularly in densely populated regions like Asia, Europe, and the North American coastline. You can see the yellow circle pointed out on the figure. While many satellites over ocean are underutilized or unused. Second, the over-ocean satellites above the northernmost Pacific and Atlantic Oceans show high utilization rates. Let's take a closer look at the second point. The phenomenon can be explained by the geodesic lines and constellations inclination. For example, in the plot is the shortest path between Beijing and LA through SLS. The yellow line represents the geodesic line, which is the ideal shortest path on sphere, while the red line shows satellite paths. Due to the 53-degree inclination limit of Starlink Shell 1, real paths are forced to be concentrated on the northernmost satellites of the constellation. Let's move to the second experiment, critical satellites removal. For this case, we remove 50 most used nodes and check the usage change. For this figure, the larger dots represent the remaining satellites, whose size and color represent the usage and usage increasing rate respectively. The green dot represents the removed satellites. The red circle pointed out the nodes with the most significant usage increase. The red arrows point out to the distant satellites that have usage increase. When critical satellites are removed, the nearby satellites experience a sharp increase in utilization. The possible reason is that these nodes take on the traffic that previously handled by the disconnected satellites. This phenomenon is most pronounced in the red circle in the figure, which is near East Asia. We can also observe that many satellites far from the removal site, such as the ones pointed out by the arrows in the figure, have significant rise in usage. This phenomenon is probably due to changes in communication paths where traffic is rerouted through those distant satellites. For this case, we remove 100 most used nodes and check the usage change. We reach the same conclusion as the case of removing 50 most used nodes. Just like utilization of nearby satellites increases, and this may due to traffic rerouted through satellites near the removed ones. And some distant satellites show high usage, and this can attribute to the increased traffic on satellites farther away. For the case of removing 200 most used satellites, we have the similar observation as the previous cases, just like the red circle and red arrows. In conclusion, we observe that utilization of nearby satellites increases. The possible reason for this observation is that traffic rerouted through satellites near the removed ones, and some distant satellites show higher usage. This phenomenon can attribute to the increased traffic on satellites farther away. To summarize our findings, satellite utilization varies widely. Many satellites, especially over oceans, are underutilized, while usage is high in densely populated regions like Asia, Europe, and North America due to ground station density. Interestingly, satellites over the northern Pacific and Atlantic are heavily used, driven by the constellation's inclination that directs traffic through these areas. And when those frequently used satellites are removed, increased loads will be put on other satellites.